Hello everyone, welcome to another video session class. So in today's class we will study about reactions and medicinal uses of imidazole. So we know imidazole is a 2 nitrogen containing 5-membered heterocyclic compound, okay, and the nitrogen is present 1 carbon difference. That means if you see the structure, this one is here 1 nitrogen and here 1 nitrogen. So we have already seen that one. So let us just start the reactions. So first reaction, that is reaction with oxidizing agent. So imidazole, if there is auto-oxidation occurs by the action of chromic acid, that is imidazole itself is stable, okay, that means that can prevent the auto-oxidation by the action of the chromic acid. However, imidazole in presence of H2O2, which is, that is hydrogen peroxide, which is also an oxidizing agent, it will undergo ring opening reaction, okay, so it will open up the ring to form the oxamide. So this is the product. So this is imidazole in presence of H2O2, oxidation will take place and it will form oxamide. That means complete ring opening will take place, okay. So this is one type of reaction. So next, this imidazole also undergoes electrophilic addition to nitrogen, okay. So the first one is protonation. There is a basic property, so it can undergo addition of proton H plus. So imidazole accept proton, so it can accept one proton to act as a base. So you just see this reaction. This is imidazole. So in aqueous solution acid will be there, so that acid will liberate H plus ion, that is proton. That proton will attack this lone pair of electron to give imidazolium cation, and it is this charge of the positive charge is resonance stable, okay. So that's why there is movement of charge in the structure. Next, another type of electrophilic addition to nitrogen reaction, that is N-alkylation. That means addition of alkyl group, either it's just methyl or ethyl, whatever, in the nitrogen, okay, or to the nitrogen. Addition of, that is known as an alkylation. That means addition of methyl group or alkyl group, any alkyl group to the nitrogen. So you just see iodine is electronegative, then your CH3 is a delta partial positive charge. So in aqueous acid, it will first CH3 will attach to the nitrogen, to the lone pair of electron of the nitrogen. So here you see it will acquire positive charge, so it is N-methyl imidazolium salt, okay. Then next, this imidazolium salt will undergo this tautomerism, not tautomerism, the resonance, that is charge will mobilize, okay. Charge will move from this position to this position, okay, this nitrogen to this nitrogen. So here what will happen, one imidazole will act as a base, okay. This another molecule of imidazole will act as a base to remove the proton, so that positive charge or H plus will be removed by another molecule of imidazole. So it will again, this one will be having, this nitrogen will be having lone pair of electrons. So again another molecule of this alkyl iodide or alkyl halide will attack to give the dimethyl or dialkyl imidazolium salt. So here the substitution or addition of alkyl will take place in 2 nitrogen, okay, 1 and 3. So it is N1 N3 dimethyl imidazolium salt, okay. So that will be the product. Then next, electrophilic substitution to carbon. So here what will happen, the favored position are 4th and 5th position, because 2 position is not favorable, okay. Because if there is addition of electrophile in the, or substitution of electrophile at the second position, there will be generation of N plus, okay, and which is very much highly unstable, okay. So that's why only the 4th and 5th position will be favorable position for electrophilic substitution, Okay, so you just see the reactions are electrophilic substitution examples are nitration. So here in presence of oleum, okay, HNO3, that is nitrating agent, so the nitration will take place either 4 or 5th, so that's why it is written 4 within bracket 5th. That means due to tautomerism the nitrogen position, nitro group position will be changed, okay, from some at one time it will be in this place and at one time it will be in this place. Okay, so that's why it is 4,5 nitroimidazole. The next reaction, electrophilic substitution reaction, is sulfonation reaction. So again here also H2SO4 is sulfonating agent. So heat it, you will get imidazole 4,5 sulfonic acid. So this is the sulfonic acid group. So the position of this sulfonic group will be changed from 4 and change within 4 and 5th position due to the tautomerism. So we have already seen, okay, in the properties. Due to tautomerism, that means shifting of this hydrogen, due to shifting of this hydrogen from this nitrogen to this nitrogen, there will be two position of this substitution, okay, electrophilic substitution, and as a result you will get imidazole 4,5. That means at some time you will get 4 sulfonic acid, at some time you will get imidazole 5 sulfonic acid. Okay, the next halogenation. So halogenation you will do bromine. So first bromination will give 2,4,5 tribromo imidazole. So here you see in the 3 position 3 carbon will be substituted with bromine. Okay, so then 4,5 bromo imidazole can be obtained by reduction of tribromo imidazole with sodium sulfide. So if you just do reduction with this sodium sulfide, you will get the 4,5 bromo imidazole. Okay, 4,5 bromo imidazole. So this will be the product. Okay, so 4 bromo 1H imidazole, or you can say 4,5 bromo imidazole. The next, imidazole catalyzed ester hydrolysis. Okay, imidazole catalyzed ester hydrolysis. So imidazole as sometimes act as an catalyst. Okay, imidazole will be reacting as a catalyst in a reaction. So here you see imidazole is used in this reaction as a base catalysis, okay, or base catalyst. So here it activates water for attack at carbonyl carbon. So this is our imidazole and it is acting as a base. Okay, it will just abstract a proton from the water and it will activate OH. Okay, then OH will attack the carbonyl carbon and the reaction will take place to give acid. Okay, so ROR. At the end of the reaction, this H will be abstracted by this RO to give one water. Again it will generate the water. Okay, ROH and water. So here in this reaction, you remember it is acting as a base catalyst or base catalysis and it activates water. Okay, so ultimately after the reaction your catalysis will be this catalytic reagent will be regenerated. You will get at the end of the reaction you will get the imidazole back. Okay, so next, imidazole as nucleophilic catalysis. So earlier we have seen imidazole is acting as a base catalysis. Here it is a nucleophilic catalyst or catalysis. So imidazole directly attacked at carbonyl carbon. So here it is directly attacking. Okay, so see, directly attacking. So this reaction is taking place, there will be displacement, and ultimately you are getting at the end of the reaction you are getting acid from the this ester. Okay, from ester you are getting acid and ultimately you are regenerating the catalyst. Okay, as imidazole as a catalyst. So we know role of the catalyst, that means after reaction it will regenerate its structure. Okay, here it will break down or whatever chemical modification will take place, but after completion of the reaction it is again regenerating itself. So this is the property of catalyst. So here also imidazole is acting as a nucleophilic catalysis. So it is next we will see the medicinal uses of imidazole. So here you see I have given 4 uses. So first one is azole antifungal agent. Okay, so all the maximum of the azole antibiotic, it will contain the structure like imidazole as a structure. So here I have given one example, that is miconazole. Then second is antihistaminic drugs. So like example is cimetidine, used to treat and prevent peptic ulcer, gastroesophageal reflux disease, GRD, and heartburn. So this cimetidine also contain imidazole as a rings within the structure. Okay, the next is antiprotozoal agents. So for example metronidazole, which is used in amoebic dysentery. So here you also see it is also containing imidazole as a ring within the structure. Okay, imidazole structure within the structure. Okay, then next another is azathioprine. So it is an immunosuppressive antimetabolite product. It is immunosuppressive antimetabolite product, which is nothing but an anti-cancer agent and immunosuppressive agent. So this is also containing imidazole as a structure in its complete structure. Okay, that is it is a derivative, we can say. These all are the derivative of imidazole. Okay, so these are the uses. So I hope you have understood. Thank you.